Hello, good morning, everyone. My name is Mqtt. I want to start my presentation with a simple story. Well, recently, as you know, usage of the IoT systems has been developed and extended during a lot of aspects of the human, like smart city, smart transport, uh, a smart uh, home, and smart health. A lot of aspects. Uh, Among these IoT systems, LoRaWAN technology with its advantages has become more in notice of developers. So it recently has been used by a lot of developers. So we saw that for interworking between this recent technology, which is LoRaWAN, communication technology, LoRaWAN, and other IoT systems, there is a drawback. So we aim to solve this problem by uh, researching and this research which I present you. The outlines are divided to overview of LoRaWAN objective, proposal, implementation, and testbed. Um, as you know, the LoRaWAN has been used a lot because it's wide uh, communication, wide, long range, and low cost communication technology. Between the IoT communication technologies, the Wi-Fi with short range power communication like Bluetooth and Zigbee, and long range communication like Sigfox and the IoT, LTE-M, and LoRaWAN ATM. Uh, they used so much. And the other novel IoT protocols are POP and Mqtt, which we used also in our mm, methodology and in our research. The overview of LoRaWAN in continue, as you can see, the LoRa protocol is located in this area, and it's long range protocol with a lot of advantages, which I mentioned in the next slide. The functionality and architecture of the LoRaWAN is like this. The sensors transmit the data to LoRaWAN gateway through LoRa protocol. Then the gateway transmit the data via internet to the backend system. The LoRaWAN backend system includes the network server, joint server, and application server, and finally user here is able to receive the data from the application server in the LoRa backend. LoRa is a low power radio access based on LoRaWAN. Many LoRaWAN backend platforms developed recently. They are free or some of them are licensed. And a user can deploy his own system located on his infrastructure, like SuperStack is a well-known local backend server, or a user can use online backend LoRaWAN backend systems provided by third-party operator. The well-known online backend is TTN. And the actual protocols between the gateway and LoRaWAN backend use LoRa mix, and it left to be implemented. They usually gateways use the Semtech protocol over UDP or MQTT. The main strength of the LoRaWAN are offer cheap end devices and possibility of deploying the private network by anyone, removing the need for a service subscription like Sigfox and NB-IoT, and decrease the operational cost for massive IoT deployments. It has a large coverage with a single gateway, more than 1,000 nodes per gateway. It provides a low power operation for end nodes. And the advantage lead to deployment of different LoRaWAN open networks. So the drawback is in terms of interoperability when the heterogeneous systems are used. So the main objectives of our research is to face the interoperability issue by proposing different interworking solutions. In case both LoRaWAN and non-LoRaWAN devices are used, integration is left to the user without any off-the-shelf technology. And when the different LoRaWAN open network are used by the same user, again, due to the heterogeneous LAN coverage, user devices may be connected to different LoRaWAN networks, which may be implemented via the different LoRaWAN software platforms with different APIs. Again, here it's left to the user side to design its infrastructure to be able to receive the data from other networks. In fact, we solved these three problems. When non-LoRaWAN devices want to connect to the LoRaWAN network, when the LoRaWAN devices want to connect to non-LoRaWAN network, and when the LoRaWAN network a lot of LoRaWAN networks want to connect to the non-LoRaWAN networks. First, we consider connecting non-LoRa device to LoRa network. Connecting a non-LoRa device is useful, where both LoRaWAN and non-LoRa devices coexist, and LoRaWAN backend is used on an application platform. Non-LoRa devices may support other connectivity technologies. It is able to connect it directly to the LoRaWAN backend. There are two solutions. Using a non-LoRaWAN interface, like platform-dependent REST API or Mqtt API, or it may be connect it to a proper virtual gateway, which we design, as you can see in the figure, acting as an interworking element, and we made it open source implementation of the virtual component, which include the virtual gateway and virtual device, and uploaded in GitHub page. And the virtual LoRaWAN device, as you can see in the figure, implement the LoRaWAN MAC and above layer, then exchange the corresponding packet with a virtual LoRaWAN gateway and a remote LoRaWAN network. Instead, virtual LoRaWAN gateway can be connected to a standard LoRaWAN network, which includes the network server, joint server, and application server, using the standard mechanisms like Mqtt or Semtech protocol. It performs the proxy functionality by relying the LoRaWAN MAC packet between some virtual devices and LoRaWAN backend system. We use the UDP as an encapsulating protocol. UDP is used in order to guarantee the easy portability on several types of devices with different access technologies. And then the gateway extract the LoRaWAN MAC packet coming from devices and forward them to the backend or LoRaWAN server. And our LoRaWAN virtual device can be used in a different application like digital twins and sidecar objects. And also physical deployment of our virtual devices is able to be made. A single element virtual device for each physical non-LoRa device, or a single element for all non-LoRa devices, providing the virtualization of these devices. Element can coincide with the IoT gateway. And the special case for connecting the co-op device to LoRaWAN network is when the non-LoRa device uses a standard application protocol like co-op or Mqtt for communicating with other nodes. The co-op connecting co-op to virtual device is divided to two scenarios. When the smart object is a co-op client, it produces and consumes the data. And when the smart object is a co-op server, it provides support for reading the data from device and writing the data to the device. In the figure, you can see the co-op smart object and the virtual device how connect to each other and transmit the data to virtual gateway, then to the LoRaWAN backend system. Connecting the MQTT device to LoRaWAN network. A smart object is a sensor in this scenario that periodically publishes data on MQTT broker. The virtual device will subscribe for corresponding topic on the same broker. Each time that the new data is published, the MQTT publish a message of a virtual device will forward it as a LoRaWAN data message to the virtual gateway that will relay it to the LoRaWAN application server. Connecting the LoRa device to non-LoRa network. Connecting LoRaWAN network to co-op agent is divided into two scenarios. Connecting the LoRaWAN network to co-op proxy, which in the scenario client forward the LoRaWAN application payload to a remote co-op server and or send back to the LoRaWAN device that will receive the data from the co-op server. In the next scenario, connecting the LoRaWAN network to co-op previous proxy, which act as an external co-op server, which you can see also in the figure in the right side. It supports put and or get methods, possibly providing also publish subscribe paradigm with the co-op observe extension. Data is retrieved from this or sent to a LoRaWAN device via LoRaWAN application server. LoRaWAN application server is located here, the component of the LoRaWAN backend sales system. And connecting the LoRaWAN network to or from a larger IoT to form a larger IoT network. But for creating a larger data-centric IoT platform, we propose architecture use publish subscribe paradigm through the Mqtt protocol and Mqtt broker for exchanging data between IoT subsystems and user clients. In LoRa network, this adapter system includes two parts. One, a client used to exchange the data with the LoRaWAN application server, and also an MQTT client used to communicate with the MQTT broker. In the figure, you can see clearly different LoRaWAN networks, backend network servers are located in this part, and then broker, which is able to receive the data and route them to the application client on the right. And the implementation section, we propose the interworking system described and the extended network architecture in a test bed and implemented it to complete the new light implementation of LoRaWAN, MAC join and answer and frame layers in Java has been realized and released as open source. To access the sensor data, we use both TTN HTTP REST API and MQTT interface. While for accessing data via MQTT, we use the standalone MQTT client. For accessing data via REST API, we developed the proper TTN client and integrated it in a new TTN to MQTT proxy. In the next slide, I will show also in a complete figure. We set a LoRaWAN backend platform based on the chip stack that we have used to connect a Raspberry Pi based LoRaWAN gateway and Arduino LoRaWAN devices. LoRaWAN sensors that we used are temperature, humidity sensors, the Arduino types, the LoRaWAN sensor devices which we prototyped the hardware with considering all possible boards like STM, Arduino, ESP32, Raspberry Pi, and a lot of other boards. And we considered all possible LoRa modules and all possible batteries we choose the best performance and the lowest power consumption and for our prototyping. Finally, we use the STM32 board as the best one, but we implemented our scenarios also in other boards like Arduino. On the same off-the-shelf gateways we used in our implementation, like a LoRa gateway, the Arduino LG02, and LoRaWAN gateway, which the Arduino in the last 8. The difference between the two is LoRa gateway just work in 2 channel, but LoRaWAN gateway work in 8 standard channel, depending on the regional parameters of each region, like Europe or United States or Australia, and it depends on the region. On the different LoRaWAN backend platforms, we implemented our scenario like LoRa local backend, like SharePoint, and online backend like IoT, which is uh, infrastructure for developing the IoT in province of Emilia-Romagna, and also a TTM platform which I mentioned before. Our test bed is like this physical sensor in the left side, the Arduino, and also the ad hoc LoRaWAN sensors, the STM32 boards connect to or transfer the data, temperature, humidity, usually to these 2 types of the gateways, and the data transmitted to the TTN LoRaWAN backend. And also from here, you can see these are 2 data generator, which generate the data. The co-op client virtual sensor and the co-op server virtual sensor are located in these 2 devices implemented, and they retrieve the data to the virtual gateway, finally retrieve the data to TPN backend server, and the data will transmit to via a TTN to Mqtt proxy to Mqtt broker, and is able to be received by user Mqtt client, and here via Mqtt device is able to receive the data again here. And in the downside, the temperature humidity sensor, the Arduino, another Arduino temperature humidity sensor, retrieve the data to verify IoT infrastructure, including the gateways and the LoRaWAN backend, LoRaWAN gateways and LoRaWAN backend server, and we are verify IoT to Mqtt proxy, which we mentioned and we implemented, retrieve the data to Mqtt broker, and again it's able to receive by Mqtt device and user application Mqtt client. Thank you very much for your attention and your time. I will be happy for any question. Thank you.